Hey everybody, we're going to take a look at a new idea, the average value of a function. And so before we get into the details, let me say a couple of quick things. This is going to be the first of many examples of us taking this idea of the integral and applying it in a new way, right? So when we started this idea a few videos back, right? The whole idea is this connection to area, okay? That connection never leaves. There's always an area in question that we should be thinking about or could be thinking about. There are often ways to interpret it differently. And we will see throughout the course of these videos that there's a style of thinking that maybe we can generalize what we did with area, where you take, when we're talking about area of these hard to conceptualize shapes like I have drawn here, our process is, well, we're taking something complicated and approximating it with a bunch of simple things, and then making a better and better approximation with the limit, right? That's what we did to find the area. We're going to use that idea over and over and over again. We'll take complicated things, make an approximation with a simple thing, and add up a bunch of little approximations, and then take a limit, and we'll see these integrals emerge. And this is going to be an example of that. There's still an area that's represented, but we're going to kind of expand that idea a little bit. And this is probably the first one we'll do in that way. So what this video is about is the average value of a function. Okay, so I've started here with, I've drawn a graph of the height of a bird. Okay, so imagine we took a video of a bird in flight, where we had a scale of how high it was, and so we traced its path. And so in the graph, time is, let's say, in seconds, and height is in meters. And this is the path that the height of the bird as it flew. And we might want to know over some interval. So let's say I pick a couple of times, like I'll call this time A and this time B. I would like to know, along this path, what is its average height over this interval? Okay, that's what we want. So let's think about what an average is. Well, when we want an average of some stuff, like scores on an exam, let's say I have 5 exams and I want to know what my average score is, I might do something, or I would do something like this. I add up all the scores and divide by how many there are, right? And I get this average score, so S-Av. Here's our issue. How many heights, right? What I want to do is add up all the heights the bird was at and divide by how many different heights it was at. But the bird was at an infinite number of heights, right? If I look at some little interval on this, if I look at, I'll draw it outside of the interval we're curious of so I don't get too messy. If I look between these two heights, let's say that represents 1 meter to 2 meters. How many heights does the bird achieve between those? Well, an infinite number, right? It hits every single real number between 1 and 2 in meters. 1.1, 1.2, 1.3, 1.1011159, 1.77344444, right? All these different numbers you can think of, and there's an infinite number between 1 and 2. And how many times does it hit heights? It's how many moments are there from A to B, right? So there's an infinite number of moments, and at these infinite number of moments, it achieves an infinite number of heights. And so that becomes difficult to add those up, right? So let's use this idea of taking something complicated and difficult, usually because of some infinity, some weird and infinite kind of thing happening, and approximate it. So what I might do is I might take my interval from A to B, and I might divide it up. Right, so don't worry about how many I've actually drawn. Let's just say I divide it up into n intervals, right? Starting at T1, T2, and on until we get to B that I'll call T sub n. So if I want to get the average height, I can approximate it by just looking at these n moments in time. It has a height of h of t1 at that first moment I've picked, h of t2 on up to h of tn, right? So these are the values of the function, right? The y value of each of these points, the height of the bird at each point along the interval, right? So imagine all those. Okay, right? So we go ahead and plug in the value, plug in the values of t for our interval. We get n heights. We add them up and we divide by n, right? No big, let me make my n's and h's very clear, very distinct from each other. So this is n on the bottom. Okay, so there's our first approximation. Now, imagine, let's pretend I did a very small interval where I only picked, let's say, 2 points, right? Well, maybe the way I split my interval up, I get this point and this point. Notice those are both kind of high on our graph. Okay, that would be a poor approximation. Or in a similar way, if maybe I picked 3 points and I got this one, and this one, those would be very low on the graph and maybe give us too low of an approximation. So the way we get better is by taking more dots, right? So more interval, more test points, more sample points where we look at the heights of the bird. And so, right, I've drawn it with many dots. We can imagine taking more and more and more of these dots. So we're getting ready for something like a limit here, but let's do a little bit of work first. First of all, I'm going to rewrite this using our summation notation. So we have first the numerator. I'm just adding up the h of t sub i's, and then dividing this sum by n. I'm just going to multiply by 1 over n out here. Okay, that's the first part. That summation is starting to look like an integral, right? Remember our integral of a function this is our definition of the integral. If you look right now, we've got this piece. I'm planning, right, to take a limit. I just talked about how I recognize if I take better and better, more and more points in the interval, I get a better approximation. So I know I want the limit. So I'm gonna do this part myself. I'm gonna add that in at some point. What we need is this delta x, and right now what we have is 1 over n. But there is a nice connection between these two. Remember the definition of delta x, the width of the whole interval divided by how many pieces you break it up into, which is what we've called n, right? The n here has the exact same meaning, right? This picture should look very familiar. Do a little bit of algebra and you get that delta x over b minus a is equal to 1 over n. Okay, so we've got 1 over n sitting here. So now I can write h average as approximately, right? Remember, this is all my approximation still. Delta x over b minus a times the sum of I equals 1 to n. Oops, in this case, it should be delta t, pardon me. Same idea. Let me just, I've just chosen a different variable name, but the same relationship holds, obviously. H of t sub I. Okay, we're almost there. Now, this expression, the summation notation, while it might be new to most of us still, remember, it's just a sum of numbers, right? These h of t sub 1, t sub 2, h of t sub 3, h of t sub n. And I'm multiplying that whole sum by this thing. I can distribute right? If I imagine multiplying this numerator by some number, I can distribute that. So I'm going to distribute the delta t. I'm going to leave the 1 over b minus a out here. So now this is going to look like 1 over b minus a h of t sub I delta t. So all I've done is distribute that delta t through the summation, right? Which is just adding up n terms, and we know how to distribute. Now I start imagining taking more and more test points, right? So here's my first approximation with all these test points. Now maybe I do twice as many, and I get a better approximation to the average. And I can just keep adding more and more points. Here's where the limit comes in. And if this limit exists, we will take that limit, what these approximations seem to be getting closer and closer to be the actual average value. In other words, this is going to be the limit as n goes to infinity, increasing the number of test points, 1 over b minus a, equal the sum from 1 to n of h t sub I delta t. 1 over b minus a is a constant, right? B and a are going to be part of our problem. If we were saying we want the average over some interval, we'll know those two numbers, right? So in this case, I wrote it on here, right? This would be maybe from 1 second to 10 seconds. Constants can slip out in front of our limits. They're not changed by the limit. And now we see something maybe not quite familiar yet, still pretty new, but should be getting familiar. That thing in there, that thing we're staring at, is the definition of the definite integral. So my 1 minus b over a is still sitting here, but this thing in here is just the definition of the integral from a to b of h of t dt. And this is what we call h average, okay? Now, this might not seem simple yet. We're new to integrals, but believe me, after a few more videos and some practice, we will be, in many cases, this is a fairly simple thing to compute, right? So we've taken this very complicated idea, averaging an infinite number of values over an infinite number of points, and come up with a fairly simple expression for it. So let me just state the definition fully without all the computation. Slide down a little bit. Let's do this here. So here's our definition. We start with a continuous function. So let f of x, I pressed a button I've never used on my pen before, and it did something funny. Let f of x be continuous on the interval ab, the closed interval. The average value of f of x over the interval, right? And this is our definition, is just, we call it f av, our f average, 1 over b minus a to b f of x dx, right? So nothing different than what I did over there, just cut through all the computation to the result. And this is our definition of the average value, okay? So, for instance, let's look at something we did in a previous video. We used our limit of sums. We took the integral, oops, we had actual values. So a couple videos back, one of the examples was the integral from 0 to 9 of x squared plus 5 dx, which of course we can write as the limit as n goes to infinity. The sum equals 1 to n of this function All right, so we did all the work, put all the expressions in there as needed, and we took this limit and got the result of 288. So you can go back to that video if you want to remind yourself how that works out. Again, this is one of the things that over the course of these videos, we will see many different methods for doing this kind of thing, and it'll become simple for us. So for now, let's just take that as computed since we did it before. And let's compute the average value, of course. So the average value, if I call this function f of x, then f average is going to be 1 over b minus a, 9 minus 0, times this integral, which is going to be 1/9 times 288 equals 32, right? So simple computation, all right? Let's give this a little bit of meaning, okay? Let's try to add some meaning to this. So let's start with, let's pretend this function f of x represents something, okay? Let's say that f of x is equal to the velocity of some object in meters per second at time x in seconds. Okay, so we input a number of seconds and we output the velocity of our function. Let's jump over to a graph of this and see what this 32 is actually telling us. Okay, I mean, we should be able to guess a little bit from how this is all set up, but here's a picture of that function, x squared plus 5. So this is our velocity function. We've got an object speeding up. Let's look at the definition of f average. So let's see, f average, whoops, there we go. F average, and I'm going to go back to our limit definition so we can see the approximation. We've got 1 over b minus a times, sorry, not the limit. We're going to go back to when it's just an approximation. 1 to n of f of x sub I delta x. Okay, this was one step in our computation, right? And this one is, I think, illustrates something important for us. So let's look at these f of x sub i's. Okay, so let's just use the simplest intervals for our example, and I'll say that my test points, my samples are just the integers. So my x sub 1 is the value x equals 1, x sub 2 is the value x equals 2, right? When I take f of x sub I times delta x, I'm looking at the height at x sub 1, and I'm multiplying it by delta x. Well, if my intervals in this case, my delta x's are, let's zoom out just ever so slightly. Oops, I went the wrong way. All right, that's pretty good. So let's look at, sorry, let me redraw that. So we pick a test point. I'm calling this x sub 1. We look at the value of the function there, and then we multiply it by delta x. And delta x in this case is just the width of these intervals, right? There's one of them. Well, if I'm multiplying this height by this width, I'm of course multiplying the area of this little rectangle. And then at x equals 2, that's x sub 2. When I multiply there, I'm doing this rectangle, right? In other words, what I'm pointing out is if I look at just this piece of this, f of x sub 1 delta x plus f of x sub 2 delta x. In this case, I'm going up to f of x sub 9 delta x. Each of these little pieces is the area of a rectangle. Okay, so our notion of area is still tied into this thing. But what does each of these areas represent? Well, if f, remember we're saying that f is the velocity of a function, we're taking the approximate velocity and we're multiplying it by delta x. That's an interval of time. So I'm pretending like this particle, whatever it is, whose velocity is constantly changing, I'm pretending it has a constant velocity on each interval. So in this first interval, it's traveling at whatever speed this is, whatever height we have here. Well, I guess we could compute that. It's x squared plus 5, so that would be a velocity of 6. I'm saying for 1 second, it's traveling 6 meters per second, right? Which will give us the distance it travels, or the approximate distance, right? Because we know it actually started a little bit slower than that. So we're getting a slightly large approximation. But we're doing the same thing here. 2 squared plus 5 gives me 9. So then for the next second, we imagine it travels 9 meters per second for that second. So we get a full 9 meters per second times 1 second equals 9 meters. So in other words, our approximation looks like we're taking 6 meters per second times 1 second gives me 6 meters. In the next second, we looked at 9 meters per second times 1 second gives me 9 meters. We do this for all of these rectangles, which represent approximate distances over each interval, right? So we add all them up. What do we get in total? We get the approximate distance this thing is traveling. In other words, let's see, I'm running out of space. Let's remove some of this writing. Hopefully we have, I'll do this. Whoops. Okay. A little more space, but I'll have to erase some of this. So what we're doing, let me try to summarize where we're at. What we're saying is when we add up this piece, f of x sub I, delta x, when we add up all of these, we get the approximate total distance traveled, right? We got the approximation over the first second, plus the approximation over the second second, plus the approximation over the third second, and so on. So we get the approximate total distance traveled. What about this piece? 1 over b minus a, this is the time that passed. Right? This is over 9, from 0 seconds to 9 seconds, meaning 9 seconds have passed. In other words, this F average, we're getting distance traveled divided by time, which is the average velocity, right? Which it should be, like that should be no surprise. If we're saying f of x is a velocity function, and we take its average, we're getting an average velocity. But we are specifically getting, I mean, just looking through this, it makes a lot of sense. Each of these approximations is an approximate distance traveled, and we're summing those up to get the approximate total distance traveled, and then we divide by how long it took. Okay, so in the case we have here, we said what this was, when we took the limits and computed the integral, we get an average velocity of 32 meters per second. Okay, so this gives us a little clue as to what the average function does. I mean, it does exactly what it says, but this, I hope, helps us see it. Let's see this one more way that's related to this. When I talk about the average velocity, right? So if I say I traveled in my car for an hour and my average velocity was 60 miles per hour, we all know that I started at 0. Or let's say, yeah, if I started at 0, we know that during the trip, sometimes I'm going faster than 60, sometimes I'm going slower, there's traffic, there's open spaces, all that kind of stuff. If I say on average, I went 60 miles per hour, another way to think about that is saying it's as if I was a car that was traveling precisely 60 miles per hour the entire time, okay? Graphically, what that means, I'm gonna clear all this stuff away. Graphically, what that means, here is the average velocity, right? 32 miles per hour. I just spent some time connecting for us this area under the velocity curve to the distance traveled. Well, if this car, let's call these cars now, if this one was traveling at a constant speed of 32, I guess we said meters per second, it's as if it would, the average velocity of 32 meters per second. So our original object whose velocity is changing traveled an average of 32 meters per second. It's saying that it moves in the 0 to 9 seconds the same amount of distance that a car traveling exactly 32 meters per second the whole time would have moved. In other words, the area under this horizontal line at 32, that's at the height of 32 over this interval, the area of that rectangle is exactly the same as the area under the curve, right? That's another way to interpret this average value geometrically. It's the height of the rectangle over that interval with the same area as the area under that curve, right? I like to think of it as if that red shape was like ice. When it melts, this is the height it will go to, ignoring the changes in volume and height as ice melts and things like that. But, you know, more or less, that's the idea. So that gives us a nice geometric interpretation, as well as, right, if it's velocity, we get average velocity as we would imagine. Okay, that is it for this one. I talked a lot, but I think that, you know, the first thing to focus on is we do just have an average value of a function formula. So knowing that formula and being able to use it is, you know, the first step to understanding this, and then start digging into those interpretations and seeing if you can wrap your head around them. And then in the background, I want us to be thinking about how we've again used this notion of the integral to take something complicated, approximate it with something simple, use a limit to get it into the precise value we want. This is a style of thinking we are going to use repeatedly throughout these videos. Okay, that is it, everybody. Thank you. I will see you next time.